This lecture is about time complexity, our lecture 12, and last time we discussed the information about collections, lists, set, and maps. Today we will start discussing the computational complexity, elementary instructions, and also big O notations and common O categories. Uh, this lecture is important for the final. There's some questions will be based on the today lecture. So, and also the recording for this lecture will be available on the Moodle and also on the YouTube. Last time we discussed a little bit about the computational complexity, and we discussed, to remind you, about some logarithmics and exponents review. One of the things is whenever we say log, always we mean log base 2. So you take log base 2 for x is equal to y. We mean by that x is equal to 2 to the power y. So if you take log base 2 for x is equal to y, this is exactly the same as log x to the base 2 is equal to y. This is equivalent as x equal to 2 to the power y. Now, the good thing about logarithm, it's growing very, very slow. So log base 2 to 1 million is less than 20. As I said, just as an exponent is growing very quickly, logarithm is growing very slowly. You can see here, this is a linear line. X is equal to n. It's growing linearly with n. And log n is growing very slow with n. Now, there's some arithmetic and math review about logarithm. If you take log a times p, this is equivalent to log a plus log p. So the multiplication inside the logarithm is equivalent to addition of two independent logarithms. If you take a logarithm for n to the power k, this is equivalent to the k and log n. So you can take the exponent outside the logarithm, as you can see, and it's become log equal to k log n. Now, log a divided by k, so if you have a division inside the logarithm, this is equivalent to subtractions of both logarithms. So if you take the numerators, you take log of a minus log of b. So you take the log of numerators minus the log of denominators. Log of log x. So if you have a log x inside log, this is equivalent to say log x. This is growing very, very slow compared to the 2 to the power 2 to the power x. So this is double exponent where you have 2 to the power 2 to the power x. As you can see, this is growing very fast, but log of log x, it's growing very, very slowly. So if you have an algorithm with time complexity is log x, you know that this is very slow algorithm, or it will not execute for a long time. Now, log x times log x, which is different from the previous one. If you have multiplication of two logs, this is equivalent to log square x. It's greater than log x for all x is greater than 2. Another math review functions are the floor functions and the ceiling functions. The floor function is retained the greater integers, not greater than x. So if you have 2.1, if you want to take floor for 2.1, the floor for 2.1 generating the largest integers not greater than 2.1. So the largest integers not greater than 2.1 is 2. If you have a ceiling for 2.1, it will retain smaller integers, not less than, I mean, smaller integers, not less than 2.1. So the smaller integers in this case is 3. You are sealing 2.1. If we discuss the computational complexity for any algorithm, for any Java program, we either look at the time complexity or space complexity. Space complexity will refer to a memory, how much the algorithm will use from the memory of your machine. Time complexity, it's about how much the algorithm will use from the execution time. Now, the time for this course, we will focus on the time complexity, so the resource for the time complexity for this. And we would like to know how much long this program will be executed. It will take log of n time, and when we say n, this is a parameter or a variable of size of the problem, and in this case is the size of the input. Now, if you consider a size of problem, then you are saying the size of the problem is always positive. You will never have the size of the problem is a negative value. So the size of input data, and most of the algorithms in this board is taking some set of data and transfer this data to another output. And in the real world scenario, sometimes you have two students, both are implementing the same algorithms, and both are providing you with the correct answers. Now, it's important for you to know that the implementation A is run faster than implementation P, and speed is very important in the real life. You need to execute some search. You would like to find the correct answer as much as quickly as you can. Most of the algorithm, as I mentioned, transfer the input object into the output object. Here, for example, we have a sorting algorithm, and this sorting algorithm is taking input data and generate the output data. Now, you can consider it's taking input objects and generate output objects. If you would like to know how much time this sorting algorithm takes to process the input and generate the output, this is where we're going to discuss today, is trying to come up with some common ground between the algorithms to decide which one of these algorithms is running faster than the other one. And we're going to use the big annotations to determine the time complexity for any algorithms. Normally, the running time for any algorithm is given by the input side. For example, you discuss the running time for this sorting algorithm if we have n input, that means n elements, array of n elements. Now, again, I repeat, the size of the problem or the size of input is always positive. We never come across the negative numbers. Let me see if you have any questions before I proceed. So, okay, these questions is still related to the lab test. It's, do you have any questions about what we discussed so far? Okay. So when we analyze the time complexity of any algorithm today, we're going to analyze it based on the size of the input. Here, for example, is an algorithm. This is an algorithm, or you can say it a method. This is a method is running an algorithm for searching. We have the input as an input array, and we have the value that we are looking for. So this is a method. It's running a search algorithms. It's called, this method called contains. It receives an input. This is an input argument. and it's received another input, it's the value that you are looking for. Now, the Boolean result is equal to false. We're going to run through the loop of all the elements inside the array, and we check element by element. If the value that we are looking for is equal to the element of array at I, then we're gonna say result is equal to true, and we break from the loop and we return result to the user. If we run for all the elements of the array and none of these elements is equal to value, then we're gonna return result. What is the initial value for result? Is equal to false. So this is a very simple search algorithms that receive an input array. Imagine now you have an input array with 5 elements. This algorithm will run very fast. You're just gonna visit all these 5 elements one by one using this for loop, and you check using if statement at each element if the value is equal to that element. If it's equal, then you're gonna set result to equal to true, and you're gonna break. You're not gonna continue looking for another element. So the first appearance of the value, you're gonna return true and you're gonna back. Now imagine if you have 1 million elements. If you have 1 million elements, then you're gonna go over all these elements until you find the one that you are looking for. If you didn't find anyone, then you waste your time. So you look for 1 million elements. That's where I am. Today we're gonna discuss how we're gonna analyze this simple algorithms in terms of time complexity to find the efficiency. Any questions? We're gonna come to the next slide to determine how we're gonna find the big O for this questions. Currently it's implement linear using the for loops. So it's only one for loop, so it's a linear. But we're gonna provide you with an informations about how you can analyze this algorithms. So the size of problem is n, is the number of elements inside this array. To examine the time complexity of algorithm, we have to set up some basic strategies that we're gonna follow to determine time complexity of any algorithms. For each line of the code, we estimate the number of elementary instructions. So what is elementary instructions? So we're gonna estimate the number of elementary instructions for each line of code. So we're gonna look at the code and we say how many elementary instructions. Now what is the elementary instruction? We're gonna discuss it later. For each line of code, we determine how many often it will be executed. So there's a strategy. First step, you're gonna go to for each line and you determine how many number of elementary instructions are there on that line. Then on the second step, you're gonna determine how often this line will be executed. Then determine the total number of elementary instruction at the end. So these are 3 steps we're gonna follow to determine the time complexity of any algorithm. Find the number of elementary for each line, how many steps this line will be executed, and also find the total. What is the elementary instructions? Elementary instruction for this course, for the purpose of this course, we're gonna simplify them. Any declaration of the variable is considered elementary instructions. Assignment is considered an elementary instructions. Addition, subtractions, divisions, mod operations, remainders, all of these consider one elementary instructions. So if you have a line of code contains assignment, then this is a one elementary instructions. If you have a comparison, greater than, less than, equal, not equal, all of these consider one elementary instructions. Boolean expression, and, or, negations, all of these consider one elementary instructions. If, else statement is considered one elementary instructions. Array access. When you mean by array access, when you want to see, I want to access element I, this is one elementary instruction. It's called read. You're gonna read from memory. Now, if you want to write to array, this is another elementary instruction, which is y to the element. and also retain statement is another elementary instructions. Elementary instruction is a basic step inside the line code, and this is the example of elementary instructions. So declaring of the variable, assignment, arithmetic addition, subtractions, divisions, and also comparisons or Boolean expressions, that is and or negations, if statement, array access, either read or write, and retain statement. All of these are elementary instructions. Now, it will be surprising, but let us assume for loop it's a single elementary instruction. So when you see the for loop, you say, okay, this is one elementary instruction. I understand inside the for loop, we're going to initialize, we're going to check the conditions, and also we're going to increment. So you have actually 3 elementary instructions inside the for loop. But now, whenever you see for loop, say, okay, I would consider it as one elementary instructions. Let us see some example. It will become more and more clear for this. But for this course, let us assume that whenever we see a for loop, we're going to consider it as one elementary instruction. Let us estimate the time complexity for the contains algorithm that we discussed at the beginning. So this is the contains an algorithms. We receive input array, we receive the value, we have the line of code. This is the line of code. Then the first, based on our strategy, we're going to go to each line of code, and we're going to determine the number of elementary instructions for each line of code. The second step of the strategy, how much often this line of code will be executed. And in the last step, we're going to add them all together. So let us see how we're going to proceed with this. So the first line, declaration of the code, declaration of the method, there's nothing there. Now, the first line is the assignment. Here we have declaring of the variable. Why we have to? Because we declared the variable and we assign. So we have 2 elementary instruction on this line of code. So we have Boolean result is equal to false. So we declare result as a variable and we do the assignment. So we have 2 elementary instructions on this line of code. The second step, we have for loop. We understand inside this for loop, we have declare the variable. We initialize it. We have comparing the variables, and also we increment. But take my word now, assume this is one elementary instruction. Whenever you see the for loop, assume this is one elementary instructions. Now, the second line is if statement. In this if statement, we have 3 elementary instructions. How we come with the 3 elementary instructions? We're going to access the array. We're going to read from element I. We read the array, we compare, equal, equal, and also we have if statement. So this is the 3 elementary instructions. Result is equal to true. This is an assignment elementary instructions. Now break is 1 elementary instructions, and we have return result is 1 elementary instructions. So these are the elementary instructions. The first step of our strategy is to go to the elementary instructions and find them out. Yes, right now, to determine the number of elementary instructions for this purpose of this course, for loop with all the assignment, with all the comparing of the array.length with increment, we're going to consider it as 1 elementary instruction for the sake of simplicity. And you're going to see that later on, this is irrelevant to determine the time complexity for this algorithms. So the first step is completed, which determine the number of elementary instructions. No, the assignment is 1. In the beginning here, we have 2. Why? Because we declare results and we assign. But here we just assign. There is no declaration of the result. The result is already declared on the first line of code. So in the assignment here, it's 1. So we go and assign the value. So let us back to the basic thing. for this course, we set up the thing. Assignment is 1, declaration is 1, for loop is 1, if statement is 1. And here in this if statement, we have 3 elementary instructions. We access the memory, we compare, and we do if statement. So this is the 3 elementary instructions. In the next strategy steps, we have to determine how often each line of code will be executed. So the first one, how often will be executed? It will be executed only once. This will be executed, assume it will be executed only once. I understand the for loop will execute it n times based on the number of elements on the array, but this will affect the one inside the for loop. So the for loop will started, assume this is one elementary instruction and it will be executed only once. Now, but if a statement, this is one inside the for loop, it will execute it up to n, which is this is the maximum. Let's assume you are looking for element inside the array, you're gonna execute it up to n. If you are looking for an element inside the array, and you're gonna execute up to n if you are not lucky. If you are lucky, you will be executed a few times and then you find your value. But let us assume the worst case scenario. The worst case scenario, if statement, if array at element I equal value will be executed up to n. That's the worst case. The true value will be executed up to 1, because if this is equal, then you're gonna go inside the if statement. Otherwise, you're not gonna go inside the if statement. The break will be executed only once. Now return result will be executed once. So in the second strategy steps, you determine the maximum number of times this statement will be executed. In the last step, you are adding up all these in the worst scenario. So you assume if something gonna run up to n, it's always gonna run to n. So you assume the worst case scenario, and based on that, you multiply the number of the elementary instructions by the number of times for each these elementary instruction is executed. So if we do this, so the first line is 2 elementary instructions and it will be executed up to 1. So this will give us 2 times 1. The second line is a for loop. We assume the for loop is 1 elementary instruction and will execute it up to 1. Now, if a statement, we assume it's 3 elementary instructions and it will run up to n. That means we are looking for a value inside the array and we are running element by element until we at the end of the day, and we are not lucky, we couldn't find our value that we are looking for, so this is up to n. The true result is equal to true, it's only 1 elementary instructions and it will execute it up to only once you find the value. Once you find the value that you are looking for, you're going to go inside the for if statement and you're going to execute this statement. And then you have the break 1 times 1 and also the result 1 times 1. Now, after we determine the number of elementary instructions and how many times these instructions will be executed, we multiply them together. Let me see if you have any questions. I see some students, they write some comments. Okay, so okay, it's better to send a message to everyone so everybody can see. The array is a 3 because you need to read from the element of the array, you need to compare, and you need to do if statement. So these are 3 elementary instructions. We define all the elementary instructions on the previous slides about what we consider as elementary instructions. Now, if you go to other reference, you might be considered some elementary instructions in different way. But for this course, and you're gonna see later on, this will not affect the big O notations. The big O notations, it will not really and precisely depend on your definition of elementary instructions. It depends on the general view and the parameter of n. You're going to see that later on. Okay. So we determine the number of elementary instruction we multiply the number of times, now we add them all together. If you do the addition, you can see that you have 3, 1, you have 3n, 1, 1, 3. So you have 3n plus 6. So you can say the time complexity or running time for the contains algorithm or contains method is a function of n. Here n is the size of input. So the function for this is equal to what? 3n plus 6. Now, if we use our previous knowledge to analyze the code in this example, so we have look at the elementary instructions on the, let me go back. We define our elementary instructions here. We define our elementary instructions, and for we make a big assumptions. We say for loop is one elementary instructions, and whenever we see for loop, we're gonna ask it's executed only once. This is a big assumption, and we're gonna stay with this big assumption, and we're gonna see how this big assumption gonna affect our calculations. And we set the number of elementary instructions and for each line of codes, and then we determine how many times this line of code will be executed. And then after we determine these two steps, we multiply the number of elementary instructions by the number of times to find out the running time as a function of n. Here when we say up to n, this n here is actually the size of the array. You receive the input array of size n, number of elements inside the array is n, and you will execute this if statement n times. That is the worst case. You are looking for an element inside the array, and this array contains n elements. You're gonna visit all the elements if you're not lucky. If you're lucky, maybe at the beginning you find it out. So the function here n is actually f of n is the running time for this contains a method is actually as a function of time of the input is equal f of n is equal 3n plus. We can plot these functions. You can have n, and here is f of n. For n is equal to 1, if you have only one element, this will cost you 9 units of time. Now, this is very important. 9 units of time. What is the 9 units of time? What is the unit of time here? It's 1 minute, it's milliseconds, or microseconds. This is depend on your machines. Some machines will run faster than the other one, but today we're gonna try to make everything as a unit of time. This is where a big O notation is coming to the pictures. We will try to find the time complexity of the algorithms independent of the machine where this algorithm is running. So if you're running this algorithm in the super machines or on the server side, or you run it in local machines, we can give you an estimations about the time complexity of these algorithms. If we use our previous knowledge to find out the running time for the following code, so we say this is the for loops, and this for loop will be executed from I is equal to 0 up to I less than n, and we increment n. Now use your knowledge. This will be one elementary instruction and will execute it for only once, but what is inside the for loop is an increment. So this code will be executed up to what? How many elementary instructions here? We're going to increment, we're going to read from the memory and assign. So you can find the time complexity for these algorithms. So this will be some constant multiplied by n. These are two for loops. So if we assume this will be executed up to 1 and this is 1, but what about this one? This statement will be executed how many times? For the first one up to n, the second one is n, so this will be executed up to n squared. So this is some constant times n squared. So that is the function of n, because you have nested two for loops. So the outer for loop will execute it for n, the inner for loop will execute it up to n, and this statement will be executed, that means is n squared. Now look at this for loop. This is a for loop is a design in different way. It's saying that from I is equal to 0 up to I less than n, and then you increment I, and you can see the initial condition here, j is equal to 0 and j is less than or equal to I. There is some typo mistake. This is a typo mistake. This is not supposed to be here. Okay, so now up to I is equal to j. So the first iteration, this statement will be executed only if I is equal to 0. Remember that whenever you have a nested for loop, the inner for loop will be executed completely for each iteration of the outer loop. So the outer loop here is I is equal to 0. When you pick I is equal to 0, the inner loop will be from j is equal to 0 to j less than or equal to 0. So it will be executed only once. Now, for the second iteration of the outer loop, I is equal to 1. I is equal to 1, j will be executed 2 times. For I is equal to 3, inner loop will be executed for 3 times. So this will be c times 1 plus 2 up to n. And this is a sequence number. This sequence number, if you try to add it, it will be equal to c n plus 1 divided by 2, or you can say it's c divided by 2 is a constant, multiplied by n squared plus n. So this is n squared plus n series. So number of times the x plus 1 will be executed n squared plus n. Any questions about how you determine the running time for these 3 examples? The last one is about inner loops. Here is the conditions for the inner loop is saying j less than or equal to I. So if the outer loop I is equal to 0, so j will start from 0 and then will end at j less than or equal to 0. So the inner loop will be executed only once. Now if I is equal to 1, the j will start from 0 less than or equal to 1. So the inner loop will be executed 2 times. The same thing, if I is equal to 2, the inner loop will be executed 3 times. So the inner loop is different from from example 2. The inner loop will always execute it up to n, but the inner loop is controlled by I, where I is actually an index for the outer loop. That's why the inner loop will be executed number of time determined on the outer loop value. Is not running free from the outer loop. Compared to the example on point 2, the inner loop is independent from the outer loop. You can see here in example 2, the inner loop is independent from the outer loop. So I does not control the inner loop. The only thing here is I is running from 0 to n and j is running from 0 to n. So both are independent from each other. But in the example number 3, the inner for loops is controlled, the upper limit of it is controlled by the outer loop. So they are dependent to each other. And this dependency gives you this sequence of executions. So when I is equal to 0, you're going to execute the inner loop only once. If I is equal to 2, this will be executed 3 times. So that's what gives you the sequence 1, 2, up to n. When I is equal to n, that means the inner loop will be executed again. And this is sequence, if you try to add it, it will give you n squared plus n. Any other questions before we proceed? Okay. Now, if we look at this example again, we have statements 1 to 3, and these are, each one of them is elementary instructions. We have, this is for loop will be executed up to in capitals, and the second for loop. So here is not nested for loops, but we have 2 independent for loops. The first for loop will be executed up to n. The second one will be executed 3 n's because they have 3 statements, and these 3 statements will be executed up to n. So the time complexity for this example is 3n plus 4n plus 3. And here, this example, the purpose of this example is to notice that there is a difference between nested for loops and disjoint for loops. Here is 2 for loops are disjoint, they are not nested for loops. So the for loops are written in sequence. You don't need to multiply them, you need to add them. And that is the difference. Most of the students are get confused here, that if you see the 2 for loops are sequence follow each other, they thought that this should be multiplication. No, the only way to multiply the for loops running time is whenever you see the nested for loops. As the previous examples here, you have nested for loop. This is a nested for loop. So the inner for loop is within the scope of the outer for loop. So these are not disjoint. That's why we have multiply the running time as n squares. But on these, they are 2 disjoint for loops, so the running time will be an addition. You add the running time. N plus 3n is 4n, and you have 3n. Now, look at this example 3. You have 2 nested for loops, one for loop and another for loop. They are 2 nested in each other. These 2 for loop are nested. And what is the time complexity for this one? I look at the index. I is equal to 1, j is equal to 1. This will run up to n capital. This will run up to n capital. So this statement, in the worst case, will be executed in square. I look at the second. This independent from the previous one. This independent from the previous 2 for loops. So this, again, I is equal to 1, running up to n. So these 4 statements, considering that each one of these statements consider only one elementary instructions, so these 4 statements will be executed up to n. So if I look at the time complexity for the first one, this will be n squared, and this will be 4n. Now I don't need to multiply them because these are 2 sequential for loops. This will be an addition. This will be n squared plus 4n. Any questions before we proceed? Okay. So now, if I ask you how many times we're gonna execute if n is equal to 10 and if n is equal to 1000. So you can, this is a function of n capital. So you take n capital and replace it with 1000, and if you take n capital, replace it with n, you find the numbers. Now, but if this is really what we need to know. So no need actually, and when you need to determine the time complexity for any algorithm or for any methods, you need to determine the exact time. So if you look here for this examples, 6n squared and 20n squared, if n is greater than or 20, is n is very large enough, and it's greater than 20, n squared is the driving the function for this. So it will not matter if you multiply n squared with 20 or you multiply it with number 6, because n squared will be the dominant for these functions. And let us consider these 2 examples. You can see here n squared divided by 2, and you see here n squared plus n divided by 2. So you see here, this is actually n squared plus n divided by 2. So n squared plus n divided by 2, or n squared plus n, you will see as n is going very large, both curves are over aligned for each other. So the dominant term is n squared over 2. Doesn't matter if you have plus constant or you plus n, because it become n squared over 2 is the dominant factors in the functions. It's derive the functions through the size of input. And most of the time, when we would like to discuss the time complexity for any algorithm, we don't need to discuss it because mostly all the algorithm will run fast for a small set. Let's say if you have 5 elements in the array or 2 elements in the array, and you'd like to search inside 2 elements of array, the time complexity will not be matter for you because you have only few elements in the array. But whenever we discuss the time complexity, we assume the worst case. Let us assume we are running a continuous algorithm that search linearly through the array where we have 1 million elements. Is that is really the worst case, when n is very, very large. What about 10 million? What about if you have a very, very large number of n, 1 billion? Now, if you have only 2 elements, all the algorithm will be the same. Doesn't matter how you implement the search algorithm because you have very few number of elements. That's why we don't need to know exactly if we have 6 times n squared or 20 times n squared, or if we have n squared plus n divided by 2, or if we have n squared divided by 2. So there is a dominant terms that we see inside the functions running time, and we have to know what is this dominant term, and this will be control the time complexity. Here is the big O notations. If you have two functions, you have function f of n and function g of n. Now, n is the size of the input. It's always positive. And both are functions of n. We say f of n is n O of g of n if and only if there exists a constant c and n0 such that for any n value greater than n0, g of n times c always greater than f of n. Any graphical representations, this is f of n, the one on the red, and the one on the light blue is g of n. You can see that f of n is actually greater than g of n for all the value less than n0. But once we are reaching n0 and moving forward, for any value greater than n0, g of n is greater than f of n with some constant, with some constant. So we say that f of n is n O of g of n if and only if we can find both conditions, n0 and c. So we are saying that g of n is bigger than f of n for all the value is greater than n0 with the help of the constant. This is the big annotation. This is where it's start everything. So the exact f of n, I don't need to know about it. I need to know it belongs to O of g of n, where O of g of n is actually a set of family of functions. We're going to see that later on. So when we count the number of elementary instruction, we assume that every elementary instruction is running with 1 unit of time, as I mentioned. So this is actually, we can say it's not true because I am running this exactly on the real life time, and this will be, might be milliseconds, will be microseconds, depend on that. But in terms of our considerations for the time complexity for this course, we don't need really to know this 3 and 6, whereas these are the factor. F of n is equal to 3n plus 6. These are actually not correct because 1 unit of time, what is 1 unit of time? It's not clear for us. So if we would like to find the big O notations for our contain algorithm, we have to look on the dominant terms inside these functions. So that's where the big O notation is coming for the to the pictures, where we actually look at the dominant terms. What is the dominant terms? So we say that the big O contains a method O of n. So all these O of n functions is linear time. So 3 of n plus 6 is actually a member of the family of n. So we can find n0, we can find a constant where this linear, what is the dominant here, is actually the dominant in this function is n. So this is belong to O of n. It's a linear time. So it's as the size of input is increased, the running time will be increased linearly with the size of input. We're gonna see in the other slide more details. So we say f of n is an element of a family of g of n. If and only if, again, we find a constant c and we find the element n0 inside the domain. And here we take the absolute value to make sure the function is gives us a positive value. We know that n is always positive because it's the size of input, and we are taking the absolute value of the n function f of n and the absolute value of g of n with the help of c to make it more like a mathematical definition for the big O notations. So if we see that we claim that the functions 3 of n plus 6 is actually a member of O of n. That means it's a linear execution time with n. How we can prove this? We say we have f of n, we have g of n, and for all n is greater than 1, f of n is always greater than 0, and g of n is always greater than 0 for all n is greater than 1. And we try to look for a constant and n 0. We can say that we have 3 of n plus 6 less than c of n. We don't know what is the c and what is n0. We can say for all n is greater than 1, you can add here, for example, n, you can say this is a 3n plus 6n, is this function should be greater than actually 3n plus 6. Is that right? So I just simply add n here. See here? And this will give me 3 of 9 of n. 3 of n plus 6 is actually less than or equal 9 of n for all n is greater than 1. You can prove that. You can take some values. Take 2. For example, this will be 6 plus 6 is 12. 12 is less than 18. Even 1, this will be 9 less than or equal to 9, which is at equal point when n node is equal to 1. So for all 3n plus 6 is less than or equal 9n for all n is greater than 1, and f of n then is a member of function of O of n. Here you prove that this 3 of n, which is the function for the contains the running time, is actually a member of O of n. And we can say that this is a member inside the linear time complexity O of n. And there is another proof for this. You can see here in this slide. I'm not going to go in detail on this one. The proof is not part of your topics, but I explain it here for sake of completeness. So you can find it out later on. So you can see here we can do the n, we divide it by 3 of n plus 6. You will give us this term. Now, again, you can say 3 of n plus 6 of n divided by n. This will give you 3 of n, 9 of n divided by n. This will give you 9, which is the constant that you are looking for here for C. So in this two slides, we prove that 3 of n plus 6 is actually it's a family, a member on the side or an element inside O of n. So the second proof used the following recipe. You can have f of n divided by g of n for c, and then you make the f of n in the top is similar to the g of n, so you can get rid of them to find the constant c. Now remember, for this recipe, you have always 1 is less than n. So if you have a constant 1, always constant 1 is less than n, where n is changed from 0 up to the last element inside your size. It's a full range. And also n is less than n squared. N squared is less than n to the power 3. So this is the fact. So for all n is greater than 1, you have 1 is less than n, and n is less than n squared. N squared is less than n to the power 3, etc. Any question before we proceed more? I'm not going to discuss this slide. I'm going to go forward to the this slide. So this slide, it's about taking this example and try to prove it, and it's very straightforward. Now, if I ask you, if you want to carry n elements, n items from one room to another room, how many operations you need? You will start thinking, I need n pickups, n forward move, n drops, and n reverse move. So I have 4 of n elements. So 4 of n is actually c times n operations. So it's a big, what is the driving factors in this function c of n? It's actually O of n. So this is an algorithm that's running with time complexity O of n. It's a linear. So if you have actually n elements, if n is increased with time, so your running time to move the elements from one room to another room will be increased. So if you start with 4 elements, will need more time if you have 10 elements. If you have 20 elements, you need more time compared to the 10 elements. So that's why we say the time that you need to move element from one room to another room is a function of n, where n is the number of elements. It's the same thing. Imagine you would try to copy an array. You have 2 arrays and you would like to copy an element from one array to another array. This is a linear time complexity. These are the big O categories, and they are sorted from the fastest to the slowest. And we have O of 1, or sometimes people they say it O of k, which is a constant running time. So what do we mean by constant running time? Can anyone suggest for us what do we mean by constant running time? I create an algorithm with constant running time. Is this a bad thing or good thing, or what does it mean for us? Any suggestions? You can unmute yourself and suggest, or you can write in the comment. If you design your algorithm with a constant time complexity, is this a bad thing or good thing? Or what is implied? My algorithm is running with a constant time. It's good actually, and it's most of the time people are looking to implement an algorithm that has running constant of time. It's independent from it. When we say running time is constant, that means it's independent from time. So if imagine you are running a search algorithm inside the array, let's say you are able to find an algorithm that can search inside the array, and this algorithm running a constant number of time, let's say 10 unit of times. Now, what is unit of time? I'm not going to define it now because let us assume it's a unit of time. Depend on the machine. If your machine is very fast, maybe it's millisecond, microsecond. So this is a good thing. So if I give you an array with 1 million elements, still I'm going to take you 10 units of time. If I give you 1 billion elements, still I'm going to take 10 units of time. So everybody in this world are looking to create an algorithm that is running with a constant time. So if you are able to see or find out an algorithm that can search inside an array with a constant time, this is a perfect choice. Because constant means independent from the size of input. This is the best case. And this is the fastest case that we ever see. Now, if you have a logarithmic, that means if I have an array of 1,228 elements, this will run 10 units of time because you have to take a log of n, log of size of n. Linear is the second best, or you can say the third best, because it's execute linear with the time. But most of the time you will have the quadratic or a cubic, and the worst case, you design an algorithm that is running exponentially with time. So imagine you are running an algorithm with an exponential. I think that this slide will explain exactly what is the best in terms of running time. So if you have a logarithmic running time, look at this column. You are running the algorithm very fast. So even if you have 256 elements inside your array, you're running 8 units of time. If you're running algorithm with running your algorithm with a logarithmic time complexity. If you have a linear time complexity, so the number of elements inside the array is equivalent to the number of units of time you need to complete the execution. So if you have 256, you need 256. If you have 8 elements, you need 8 elements. That is for the linear time complexity. Now what about if I have n log n? N log n, you have to take n log n multiply with each other. So you can see the time complexity of n log n. It's worse compared to n, and is very worse compared to the algorithm. So the n log n, it's worse than the linear. So n log n, it's worse. So if you have an array of 256, actually you need 2048 units of time to be executing this algorithm. So if you're trying to looking for an element inside the array, or trying to sort the array, or whatever is the algorithm, and if this algorithm is running n log n, then it's worse than the linear, it's worse than the logarithm. Look at now at the quadratic. Imagine you are running for an array of 256, you need 65,536 units of time. It's very worse compared to n log n. It's very, very worse compared to logarithm. And look at n to the cubic, it's very worse. So for 256 element, you need around, I believe, 16 million units of time. This is the exponent. The exponent is the one of the worst algorithms. So try to avoid, whenever you try to program something and you come up with a method for your algorithm, try to avoid having exponent time complexity. You can see here for even 32 elements, you are 4.3 times 10 to the power 9. Is very worse unit of time. So in summary, if we design our algorithm, is the best that we are running in logarithm time complexity. And the best of the best is a constant time complexity, independent from the input. Big O is describe the algorithm that is running constant with time. Running time does not depend on the size of input. Like get inside array list. You give the index, I want to get element 0. So it will go to the element 0 and find it out. So this kind of time complexity contains for the hash set. That's why I told you hash set is better than a tree set. So because contains, if you want to test, if the element is there inside the hash set, you only need a constant. So it doesn't matter how much the size of the set in the hash set, you only need constant time complexity to execute contains to test if the element is a member of that set or not. If you want to get element from the array set and you provide the index of that element, it's very quick because the array set is used implicitly the index to search inside that array. So you want to go get element number 11. So it will go to element number 11 directly and find it out. In log n, I mean logarithmic times, not in log n, sorry, log n, It describes an algorithm that running proportional with the logarithm of size of input. And there is like a binary search. Binary search inside the sorted array. If you try to run inside the sorted array, and this is a binary search, this will give you log of n. Look at the contains inside the tree set. It contains inside the tree set here, it's actually n log, log n, which is a logarithmic. So if you have a tree set of size of n element, the contains will take log of n to be executed. These are examples for the for loops, and you can see the for loops. The I started from 1 up to n, and the increment is 2 times n. So the for loop is not incremented by 1, is actually multiplied by 2 at each time. So you start from I, and then the next iteration I is equal to 2, the next iteration I is equal to 4. So this will be like this: I is equal to 1, I is equal to 2, I is equal to 4, at 4 it's 8, and this will continue. So this will be like 1 plus log n its number of iterations. If you execute these algorithms, because the increment here is not addition or increment or decrement, it's actually I equal I times 2. So each time you multiply I by 2, you make a jump. So you start from 1, you go to the 2, then you make a jump to 4, then you make a jump to 8. From 8, you go to 16. So you make a jump. You're not going sequential through I from 1 up to n. So that is equivalent to n is equal to what? Log of n. So this is actually an example for a for loop with the running time of this for loop is a logarithmic time complexity. Now, this logarithmic time complexity, just to demonstrate, we already saw that, it's running very fast with the size of input. So even if you have a very huge amount of data, let's say if you have n is equal to 2 to the power 60, which is equivalent to 10 to the power 18, the size of universe, the running time is 16 units of time. It's very fast. So even if you have a large or a huge amount of data, you need to process it through your algorithm, and your algorithm is running with a logarithmic time complexity. This is very, very fast. O of n is a linear time complexity. We call it, so contains an unsorted array is the example that we discussed at the beginning of this lecture. Contains, we have to visit all the elements, and once we find the element, we return true. This is an example. Finding the minimum or the maximum value inside the array or a list is actually a linear time complexity. This is an example of linear time complexity. For any algorithm for loops contain a sequence of operations O of n, and it's running, you see here the increment plus plus. So you are going from 0, 1, 2, 3, 4. You're not making any jump. You take only one step, 0, 1. So you are running linear with time. N log n is a logarithmic linear logarithm, a time complexity. It's a linear times logarithmic time complexity. It's worse than linear. It's worse than logarithm, but it's better than n squared. And this is an efficient for sorting an array. Most of the sorting arrays or a list algorithm is actually a log n algorithms. A quadratic algorithm, it's worse. So if you size of input is increased, it will be n squared. So you can see if your size of array is 8 elements, it will move to 8 squares elements. So this is most of the time nested for loops has a time complexity, a quadratic time complexity. Here is n squares or n times n, where m is different, but whenever you assume m is equal to n, you will receive n squares. And these are also the time complexity quadratic. Even if the I index here, you can see the inner loop is controlled by I. So you start from j is equal to I plus 1 up to n. Still this is running as n minus 1 plus n minus 2 plus up to 0. and this will also give you time complexity, square time complexity. 2 to the power n is exponent, is the last one we're gonna discuss today. Exponent time complexity is the worst case, and it's trying, for example, to break down the password. You don't know the password and you forget your password. If you try to figure it out, is actually complexity of that algorithm normally is exponential time complexity, and it's recommended to avoid this. So it's running very fast. Imagine you have a size of input is 60, you need 2 to the power 60, which is actually a very huge amount of unit of time, which is actually the time or the age of the universe. So avoid designing an algorithm that run with a time complexity exponent. So I will stop up to here. This is our last slide. You can even figure out the graph here. You can see n. This is n log n. This is O of n squares, and this is 2 to the power n. I will stop the lectures here, and I will be open for any questions if you would like to ask any questions. I recommend all of you to read the slide. You can see on this slide is very good slide where we say that 3n squared plus 17 is n of n. And we can say 3 of n squared plus 17 is O of n squared. That means it's an element on O of n squared. And we can say 3n squared is equal O of n, and 3n squared plus 17 is a members inside this family. But we cannot say O of n is equal to 3n squared plus 17. So this is very important here before I close, is we cannot have the left hand side is O of n. You see here, this is a difference between saying 3 of n squared plus 17 is equivalent or equal to O of n. But we cannot say O of n squared is equal to 3n squared plus 17. We never say this, so keep that in your mind. I will stop the recording.